So now that we've gone through these exponential and logarithmic functions with base e, we've gone through their applications. We now want to generalize this, and we want to see what are the derivatives of just a to the x and log base a to the x. So they're really nice when it's the natural base or natural log, and we're going to utilize that to our advantage. So first, because e and natural log cancel, e to the ln of a, those cancel, just give you a. So what we're going to do is we're going to look at the function a to the x. So since a can be written as this, it's the same thing as e to the ln of a to the x power. And when you have a power to a power, you just multiply those two exponents. Okay. So now we're going to apply the chain rule to differentiate both sides. So the derivative with respect to x of a to the x, which is here, is the derivative with respect to x of this, which we know is just itself, and then because it's not just x up top, we've got to apply chain rule. So the derivative of e to the x is always e to whatever you had there before, but now chain rule tells you you have to take the derivative of the exponent as well. So when you differentiate x natural log of a, ln of a is just going to be a number. It's going to be ln of 2, ln of 3, whatever it is. It's just that constant. And then you get the e to the x ln of a back. But this e to the x ln of a is what we have here. It's just a to the x. So this becomes ln of a times a to the x. So our special rule for differentiating any exponential function is the derivative with respect to x is a to the x times ln of a. So you get that natural log of the base attached to it. So let's go through a few different examples. We'll start with some simple ones and then we'll make it a little more complicated. So first we want to take the derivative of y equals 7 to the x. So you're still going to get exactly the exponential back, but you have to times it by the natural log of the base. So its derivative is still 7 to the x times the natural log of 7. In the case we have e to the x, we've already done this, but you can see it still fits the pattern. You get e to the x times the natural log of the base. But the natural log of e is just 1, so this is just a very special instance where you get e to the x back. Okay. Now if we try to combine these functions, I no longer have just x up here, so when I take the derivative of this exponential function, I've got to apply chain rule. So you still get exactly the exponential function back. You multiply by the natural log of base, but chain rule tells you you have to differentiate by the exponent as well. So the derivative of 1.5 times x is just going to be 1.5. Okay? So all the same rules still apply. Now just when we have a different base, you've got to add the natural log of the base to it as well. So now that we have the derivative of the normal logarithmic function and the derivative of this arbitrary exponential function, we're going to use that to differentiate log base a of x. So if you remember, if we rewrite this, our base is a, our answer is x, and then y becomes the exponent. So that's that bacon and eggs. So it's equivalent to this, and we're going to take the derivative with respect to x of both sides. Okay? So what that gives us on the left-hand side is you still get a to the y back. You get natural log of the base, but because you have a y up here, let me bring what was there. Because you have this y up here, implicit differentiation tells you get that y prime or dy dx attached. And then the derivative with respect to x of x is just 1. Okay? So I'm solving for this derivative. I'm going to go ahead and just divide both sides by this a to the y ln of a. And so that gives us the derivative of y with respect to x is 1 over a to the y ln of a. But a to the y is just x, so this is 1 over x ln of a. So just like the derivative of the exponential or the natural log, you get 1 over the inside, but now you have to times it by the natural log of the base. So pretty much for anything other than e, you're going to get natural log of the base attached to the x. So you see it's in the denominator with the x. Right? So let's use that. Let's go through a bunch of problems and get some practice. We've got 1 over log base 8 of x. So you still get 1 over the inside function, but now you have to multiply by the natural log of the base. If you have just log of x, you still get 1 over x, but it's not natural log. If there's no number there, it tells you it's base 10. So it's 1 over natural log of 10. Okay. And now here, if we spice it up a little bit, this is no longer just x inside, but when I go to differentiate it, same process, you get 1 over the inside function. You have to times it by the natural log of the base. And then chain rule tells you have to take the derivative of the inside as well. So you have to take the derivative of x squared plus 2x. So if you do that, derivative of x squared plus 2x is just 2x plus 2. So the derivative of this exponential function is this whole thing here. Okay. So let's try one more. Make it even more complicated. We've got the product of two functions. One of them is an exponential, one of them is a logarithmic. So we've got to go ahead and use product rule. So you get the first function times the derivative of the second, plus the second function times the derivative of the first. So for each of these, they have a base other than e, so we have to remember to attach the natural log of the base. So this first piece stays alone. For log of base 4 of 6x plus 6, you get 1 over that inside function, and then you have to multiply by the natural log of the base. And now, adding chain rule into that, you have to multiply by the derivative of the inside. Okay. For the second one, we keep the log alone, and we have to differentiate the exponential function. So you still get exactly the same exponential function back. You have to multiply by the natural log of the base, and chain rule tells you you have to multiply by the derivative of the inside as well. Okay. So now we can kind of clean all of this up. The derivative of 6x plus 5 is just 6. So I'm going to get 6 times the exponential over the same denominator. And then for the second piece, the log stays alone, the exponential's there, the ln of 5's there, and then the derivative of 2x to the third minus 1 is just applying power rule, it's 6x squared. Okay. So the last application we want to do is about annuities. So if you've ever heard of an annuity before, basically if you have a savings account which you regularly make deposits into, that's called an annuity. So we have a nice formula, if you remember back to our interest way at the beginning of this semester, when you had it compounded at certain times, we knew how to figure out the amount in the account. So a whole lot of words coming on right here, but if we let P be the amount paid into the annuity on a regular basis, so basically it's what your payments are. R is the interest rate, and it's the annual interest rate, which you want to enter as a decimal. N is the number of times you're going to compound the interest, and T is the time in years. So this formula, the 1 plus R over N to the NT, was how we found the interest when you had it compounded N times a year. So all that is now we're multiplying it by the amount of payments that are going at a certain time, and we have to divide it by this R over N. So you can take a look in your book to see more so where this comes from. You don't need to know this formula off the top of your head. But the A is just the amount in your account at any given time. P is the amount of money you make in payments. R is your rate as a decimal. N is the number of times this gets compounded, so monthly, quarterly, biweekly, whatever. And T is the time in years. So this is how we find how much is in the annuity. So let's assume you're going to open a retirement savings account. You're going to deposit $200 every month, and it's got an interest rate of 4.2% that's compounded monthly. So we want to see what is the amount in our account after 2 years. So we're given a bunch of information. The monthly deposit we're making is $200. The rate is 4.2, which is 0.04, and it's compounded monthly, so N is equal to 12. So if we plug all of this into the formula we have for our amount in our annuity, we have P, we have our rate in 2 locations, we have N is 12 for monthly, and then T is going to vary. So if you simplify that a little bit, you'll get this expression. And then going through, if you take 200 and divide it by 0.0035, you're going to get this amount. So this is how much is in our account after T years. So we want to see, after 8 years, how much do we have in our savings account when we're making this $200 deposit per month. So all we do is replace T by 8. And if you plug that into a calculator, after 8 years, you're going to have a little less than $23,000 in your account. Okay? Now what we want to see is what is the rate of change in the value of our account after 8 years. So essentially, if we want that rate of change, we want to see what is the derivative at 8 years. So we've got to go ahead and take the derivative of A of T. So first, let's start by rewriting it. So here is our function. All I've done is I've distributed this 5,000 to make our lives a little bit simpler. So this is the 1 times the 5,000, $57,142. And now we want to take the derivative of this. So it is an exponential function. This is just a constant, so it stays attached. The derivative of this exponential function is you get exactly that function back times natural log of the base, and then chain rule, because it's not just a t exponent, you have to multiply by the derivative of 12t. And then for this particular piece, it's just a constant. It has no rate of change, so really you add 0. Makes no difference to it. Okay? So now what we need to do, the derivative of 12t is just going to be 12. So everything stays the same and you multiply it by 12. You could go through and try to simplify this if you want, but there's no need, because all I want to do is I want to see what is the rate of change after 8 years. So you want to plug in t equals 8, which just means you're replacing t by 8. And so you're going to get, this is about $3,350.58. So after 8 years, your rate of change is $3,350.58. So that's what its rate is per year.